Welcome to this advanced technical training video on BESS fire suppression systems and fire alarm control panels. My name is Tony Rogers, and in this comprehensive training, we will explore the intricate details of these systems, including the detection and management of gases such as hydrogen, carbon dioxide, and carbon monoxide, temperature and UVR monitoring, fiber optic communication and FACP, advanced alarming features, magnetic current switches, pressure switches, electrical and mechanical formulas, considerations for water tower placement, fire resistance insulation materials, and the negative aspects of certain design considerations. Gas detection and management. Gas detection plays a crucial role in fire suppression systems as it enables the early detection of hazardous gases and facilitates timely response actions. BESS fire suppression systems utilize advanced gas sensors to detect hydrogen, carbon dioxide, and carbon monoxide. The concentration of gases in the protected area is measured using sensors, and the information is processed by the fire alarm control panel. Let's examine the gas detection formulas. Gas levels, ppm, equals sensor output minus zero level divided by the sensitivity factor. This formula is used to calculate the concentration of each gas based on the sensor output, zero level, and sensitivity factor. Hydrogen detection. Hydrogen is a highly flammable gas that poses a significant fire risk. Gas sensors accurately detect hydrogen levels and trigger appropriate response actions to mitigate the danger. Carbon dioxide detection. Carbon dioxide is a byproduct of combustion processes, and its accumulation in enclosed spaces can displace oxygen, leading to asphyxiation. Gas sensors monitor carbon dioxide levels to ensure occupant safety. Carbon monoxide detection. Carbon monoxide is a toxic gas produced during incomplete combustion. It is odorless and colorless, making it particularly dangerous. Gas sensors detect carbon monoxide levels and initiate appropriate measures to safeguard occupants. Temperature and UVR monitoring. Effective fire suppression systems also incorporate temperature and ultraviolet radiation, UVR monitoring to enhance fire detection capabilities. Temperature sensors detect abnormal increases in ambient temperature, signaling potential fire events. UVR sensors detect the presence of ultraviolet radiation, which can indicate the presence of an open flame or arcing. By monitoring these parameters, the fire suppression system can rapidly respond to fire incidents. Fiber optic communication in the fire alarm control panel. Fiber optic communication plays a pivotal role in fire alarm control panels for reliable data transmission and advanced alarming features. Fiber optics offer several advantages over traditional copper-based communication systems, including faster data transmission. Fiber optic cables can transmit data at significantly higher speeds, ensuring real-time information flow within the fire suppression system. Immunity to electromagnetic interference. Fiber optic communication is immune to electromagnetic interference, ensuring uninterrupted data transmission and reducing the risk of false alarms. Increased signal integrity. Fiber optics maintain signal integrity over longer distances compared to copper cables, enabling communication over larger fire suppression system installations. Advanced alarming features. Fiber optic communication enables advanced alarming features in the fire alarm control panel, providing enhanced situational awareness and streamlined system management. Some notable features include remote monitoring. The fire alarm control panel can be remotely monitored, allowing off-site personnel to receive real-time updates on system status and respond promptly to any issues. Event logging. The fire alarm control panel logs events and system activities, aiding in post-incident analysis, troubleshooting, and system performance evaluation. Real-time system status updates. Fiber optic communication facilitates the instantaneous transmission of system status updates, enabling quick decision-making during emergency situations. Magnetic current switches and pressure switches. Magnetic current switches and pressure switches are utilized to monitor the live status and operational state of dampers and fans. Magnetic current switches employ magnetic fields to detect the presence of current flowing through a circuit. These switches are commonly used in fire suppression systems to monitor the activation and deactivation of dampers and fans. When current flows through the circuit, the magnetic field is generated, causing the switch to close and indicate the live status of the equipment. Conversely, when there is no current flow, the magnetic field diminishes and the switch opens, indicating the equipment's inactive state. Pressure switches, on the other hand, are employed to monitor the pressure within ductwork or other parts of the fire suppression system. These switches consist of a diaphragm or spring-loaded mechanism that responds to pressure changes. When the pressure exceeds or falls below a specified threshold, the switch activates or deactivates accordingly, signaling the operational state of the system. Electrical and mechanical formulas. Accurate calculations are essential in designing and implementing fire suppression systems. Here are some key electrical and mechanical formulas used in system design. Cubic feet per minute. CFM calculations determine the required ventilation for efficient heat dissipation and maintaining safe environmental conditions. The formula for CFM is CFM equals the area multiplied by the air changes per hour multiplied by the room height divided by 60. This formula takes into account the size of the protected area, desired air changes per hour, and the room's height. Duct sizing. Proper duct sizing ensures adequate airflow within the system. The formula for duct diameter is duct diameter equals the square root of 4x CFM divided by pi multiplied by velocity. This formula considers the cubic feet per minute and the desired airflow velocity to determine the appropriate duct diameter. Water tower placement considerations. Water tower placement is a critical aspect of fire suppression system design. Collaborating with the local authority having jurisdiction, AHJ, and fire marshal is crucial for obtaining valuable insights into prevailing wind directions and patterns. By analyzing these wind patterns, water towers can be strategically positioned to maximize the dispersion of water mist during firefighting operations. This collaborative approach ensures that water is effectively directed towards the adjacent BESS containers, thus mitigating the spread of the fire and aiding in its suppression. Fire resistance insulation materials. Fire resistance insulation materials such as triphenyl phosphate, TPP, are incorporated into our fire suppression systems to mitigate thermal runaway and protect critical components. These materials act as flame retardants, releasing phosphorus compounds when exposed to heat. The released compounds create a protective char layer that inhibits further combustion, providing additional time for occupants to evacuate and firefighters to suppress the fire effectively. Negative aspects of design considerations. While considering design aspects, it is important to be aware of potential limitations and drawbacks. Let's delve into the specific negative aspects of magnetic switches and pressure sensing circuits. Magnetic switches. Although magnetic switches are widely used in fire suppression systems for their simplicity and reliability, they are not without their challenges. One potential concern is their vulnerability to external magnetic fields, which can interfere with their operation and lead to false readings. These external magnetic fields may emanate from nearby equipment, electrical systems, or even natural sources. In addition to magnetic field interference, another issue that may arise is vibration or seismic activity. Vibrations can cause the magnetic switch contacts to open or close unintentionally, leading to erroneous live status indications. Similarly, during seismic events, the movement and shaking can disrupt the proper functioning of magnetic switches, compromising their reliability. To mitigate these risks, careful consideration must be given to the location and installation of magnetic switches. Shielding measures, such as using non-magnetic materials or enclosures, can help minimize the impact of external magnetic fields. Additionally, implementing vibration dampening techniques or utilizing seismic-resistant mounting mechanisms can help maintain the stability and accuracy of magnetic switches in dynamic environments. Pressure sensing circuits. Pressure sensing circuits are essential components in fire suppression systems for monitoring the pressure levels within ductwork or other system components. However, they are not immune to certain challenges that may affect their performance and reliability. One common issue with pressure sensing circuits is the potential for clogging. Over time, dust, debris, or particulate matter can accumulate within the pressure sensing lines, obstructing the flow of air or gas and impacting the accuracy of pressure measurements. Regular maintenance and periodic cleaning of the sensing lines are necessary to prevent clogging and ensure accurate pressure readings. Calibration is another critical aspect to consider with pressure sensing circuits. Over time, these circuits may experience drift, resulting in inaccurate pressure readings. This drift can be caused by factors such as environmental changes, mechanical wear and tear, or aging of the sensing components. Regular calibration of the pressure sensing circuits is essential to maintain their accuracy and reliability. Calibration should be performed using calibrated reference instruments and following established procedures to ensure precise pressure measurements. Additionally, it is important to consider the range and sensitivity of pressure sensing circuits. If the selected pressure range is too narrow or the sensitivity is not appropriately adjusted, the system may not effectively detect variations in pressure, leading to false readings or inadequate response actions. By understanding the intricate details and trade-offs associated with these design considerations, fire protection engineers can make informed decisions to optimize system performance, safety, and reliability. Thank you for joining us in this advanced technical training video. We hope that the detailed information provided will empower you in your role as a fire protection engineer, enabling you to design and implement efficient and reliable fire suppression systems.